All right, so I want to give the last lecture over this intro note guide over resolving vectors. I'm going to go down to, I think this is the third page, and where we talk about resolving vectors into components. Pretty much what this means is that we are going to split a vector into its parts. So if we write the definition for resolving a vector, we are going to split a vector into its x part and its y part. Instead of using the word part, we say component, right? It's x component and its y component. And the idea, by doing this, the idea is that a theme of this chapter, and this is kind of what we're after here, is the theme of this chapter is that when an object is in motion, its motion, an object's motion can be discussed, can be analyzed, can be, we'll say can be analyzed and thought about, or analyzed and it can be studied, right? I think we just leave it there with analyzed. An object's motion can be analyzed independently. Its x motion can be analyzed independently from its y motion. So an object's motions can be analyzed in each direction independently. Independently of the other direction. And the bridge between the directions, and this is going a little bit beyond what we need to know for today, the bridge between the x and the y direction is going to be time. All right. So we'll kind of leave that there about the bridge being time right now, and we'll look at an example. Up here, I know we left some blanks, and that's probably fine. Components are chosen to be along the x and y axis. An important thing with that is that your components will make up a 90-degree angle. So the angle between them will be 90. I'll explain what that means here in a second. Components have a positive or negative sign. This is kind of important right here. Components are drawn with dotted lines. All right, good. Okay, let's move on here. I think this is one of those things where just doing some examples helps more than anything. All right, this first example, what it says here, find the components of the following vector. So here we have a vector. It is a velocity vector worth 95 kilometers per hour at 35 degrees, say, above the horizontal. We want to know how much of that velocity is directed in the x direction and how much of it is directed in the y direction. Okay, so the way we do this is, let me switch pen color here, is that we split this up. This vector, and I'll go ahead and draw it maybe in orange. This orange vector, right, is directed up and right. So we know that a piece of that motion is going to be going right, and we draw a dotted line just like that, and that's going to be its x component. So we'll call that Vx, and a piece of its velocity is going to be directed up, and we'll call that Vy. Now, because we know something about angles, this 35 degrees is closer to the horizontal than it is to the vertical. So this more of its velocity is going to be in the x direction, right? I think that that's a safe prediction. That what I'm saying is a safe prediction that Vx will be larger. Larger than what? Larger than Vy. Now, it won't be as large as 95. And we know that because the x component and the y component have a 90-degree angle between them, right? Because that's the angle between the x direction and the y direction. It's 90 degrees. Okay, so we have, now you can see, this should remind you of SOHCAHTOA. We have an angle. It's 35 degrees. We'll call that theta. And we want to solve for Vx and Vy. How do we start, right? Well, we'll start by labeling our triangle. I think that's the safest way. Pick a different color here. I guess we'll go red here. All right, across from 90 is going to be my hip. So V is going to be the hip. Across from theta is going to be my opposite. Next to theta is going to be my adjacent. All right, so we want to solve for all of these. So when you solve for these, you always want to write out your formula. It doesn't matter which one. We're going to end up using sine and cosine. There are other ways to do it. This is always the most straightforward, and this is the way I always choose to do these problems. We want to solve for an opposite and an adjacent. So let's go ahead and solve for the opposite first. To use the sine formula, we need to know the hypotenuse and the angle. If we have that, we can get the opposite. So I'll go ahead and plug in everything we know. We can say, whoops, I'm still in red here. Let's go back to black. All right, we can say sine of 35 degrees is equal to the opposite, which is Vy, divided by the hypotenuse, which is V. Now you can go ahead and plug in the number for the hypotenuse, but I'm going to go ahead and go a step further, right? And just leave it the way it is. I'll leave it the way it is. What the heck? All right, so we'll go ahead and multiply both sides by V. And we're left seeing that Vy is going to equal, let's write it right here, the hip sine the angle. And we know that the hip, V, is equal to 95 kilometers per hour. Now you might be sitting there saying, well, do we have to switch to meters per second? And the answer there is no, we don't have to. But just realize that when we solve for Vx and Vy, we'll be getting kilometers per hour. All right, so I'm going to write that in with the units. All right, so we have something like that. Once again, our calculator's got to be in degrees, so I can plug this in my calculator. I believe I'm in degrees. I better check really quick. Yep. Okay. 95 sine 35 is equal to 54.49. Units here are going to be kilometers per hour. All right, and that is one of our components right there. Okay, so we used SOHCAHTOA, specifically SOH, right? Sine equals op over hip to solve for Vy because Vy is an opposite. So I'm just going to go ahead and write that answer right up here. Something else worth noticing is that if you're going to make, say, up as positive and down as negative and right is positive and left is negative, then it would make sense that the 54.49 would have a positive sign, right? Because we can see that Vy is directed up. Okay, let's go ahead and get the next one. Cosine of theta is equal to, the adjacent is Vx divided by the hip, which is V. I'm resisting the urge to put numbers in right away, just because I think it's kind of neat sometimes when we don't. Sometimes you can see stuff that isn't directly obvious. So what we're seeing is that Vx is equal to the hip cos the angle, right? That's really what this is. That the adjacent Vx is equal to the hip cos the angle, right? That's really what I have here, right? I have the adjacent equals the hip cosine theta. Okay, let's go ahead and plug numbers in. So we know that Vx then is equal to 95 kilometers per hour times the cosine of 35 degrees. Now the cosine of 35, I know for a fact, is going to be a larger number than the sine of 35. So this is definitely going to be a larger answer here than we got before. 95 cos 35 is equal to 77.819. So we're going to say 0.82 kilometers per hour. 77.82. Okay, let's go ahead and add that up top. Let's see here. Kind of running a little low on room. Once again, this will have a positive sign. I know I'm making my kilometer with a lowercase k. I apologize. All right, so there we have it. Those are our two vectors. One thing you should notice is that when I drew the two blue dotted lines, did you notice that I drew them head to tail? Because you should have. That's important right there, right? What that's saying is that Vx plus Vy is equal to V, right? That if we add 77.82 plus 54.49, we get 95. No, that's nonsense. That's not what I'm saying. What I'm saying, though, is that this Vx, this dotted blue line, plus Vy in vector addition, right? If we put them, let me get a highlighter here. If we put them head to tail, right, that the resultant points from the start right here to the end. And then this orange vector, which I'm now changing it back to black, is the resultant. So our resultant was what we started with. And then we split it up into its two parts. So that's really what we're doing here. So why doesn't 77, if I'm saying that vector Vx plus vector Vy equals V, right? That's what I'm saying, right? Let me write that out. I'm saying right by vector addition. That's what I'm saying. And then how come the magnitudes, the numbers 77.82 kilometers per hour plus 54.49 actually total up to, I don't know, about 129, 130? Yeah, a little over 130. Well, let's think about why that is. This is a right triangle, right? So if we want to solve for 95, what we would say then is this. We would say that 77, I'll start there. 77.82 squared plus 54.49 squared is equal to 95 squared. That is true. All right, so you can see Pythagorean theorem coming up again here, right? And how these vectors are related. Okay, so really, like the last few days, what we've been working on this week, it's all kind of culminating now in resolving this vector into its parts. Okay, good. All right, so I have my answer there. And I always like to include a direction. Once again, these are both positive. You could say up here for y. You could say right here for x, right? If you want to put a direction that is not positive or negative, either one is okay. Just by having the positive sign, that's good enough. But sometimes I like to have a little more than that, just to point that out. Okay. Example 2. Find the components of the following vector. Draw the components and report their values. All right, so on this one, let's go ahead and dotted line these in, right? Now this time, this vector is going up and left. Notice it's 80 kilometers per hour, but it's going to be made of a negative x component that points left. And it's going to be made of a positive y component, which points up. You do not have to worry about the signs. You apply the sign at the end if you like, but remember that the sign negative for the x component just means left. The sign positive for the y component just means up. All right, I'm going to go ahead and label these. This is Vx. This is Vy. Once again, we don't have to worry about the signs right now. We're just solving for the sides of this right triangle. Let's go ahead and put the right angle in. Always between the x component and the y component. Notice that Vx and Vy are head to tail. They add up to the resultant, which is V. Good, let's go ahead and label our triangle. Across from 90 is our hip, that's 80. Across from 30 degrees is Vy, which is our opposite. And next to 30 degrees is Vx, which is our adjacent. All right, good. Write your equations. What variable are you solving for? All right, we'll just pick one to solve for. Doesn't matter what we're going to solve for first. We'll stick with the opposite again. So write our equation down, right? This is where we use SOHCAHTOA. SOHCAHTOA helps us remember our equations. So we just spell it out like this. All right, the first one is going to have an opposite, a hip, and a theta. So that would be opposite hip theta, opposite, hip, and theta in the sign. So we're going to have to use SOH. SOH, when we write it, looks like this. SOH. See it? SOH. And that's how we know to use that formula. All right. Let's go ahead and plug in our values. So we can see now sine 30 is equal to the opposite, which is Vy, over the hip, which is V, which is also equal to 80 kilometers per hour. All right, let's kick the 80 kilometers per hour to the other side. Let's multiply both sides by 80 kilometers per hour. Cancel our 80s. All right, this is over 1. Cancel our kilometers per hour. And we're left with Vy is equal to 80 kilometers per hour times the sine of 30. Now, sine of 30 is one of the special angles. It's similar to cosine of 60. Sine 30 is actually equal to 1/2. So what I'm saying is we can do this in our heads. Half of 80 is 40. All right, there we are. Once again, we're using kilometers per hour, and that's fine. How do you know like when to keep it in kilometers per hour and when to switch it to meters per second? well, you always want your units to agree. And there's certain times in this class, which I think will be obvious when we have to change it into meters per second. And I'll try and point those out when we get to them. Okay, let's do the other one. The other one involves the adjacent, the hip, and theta. So we're going to use ka part of SOHCAHTOA. You might say, well, we have the opposite. Can we use tan? Right, because we know the op is, what do we say, 40 kilometers per hour? Go ahead and write that in. Yeah, you could use tan now. But I always do it the same way to try and keep it more straightforward for the students. And that way we're always doing the same same routine resolving vectors. And it keeps it easier. So we're going to use Ka, C-A-H, right? C-A-H. Okay. This is telling us cosine theta is equal to the adjacent over the hip. Notice that when we use SOHCAHTOA, the order is always the same, right? S-O-H, C-A-H. Just like that. All right, let's go ahead and plug in what we got. Cosine of 30. Cosine of 30 is a rough one. It's actually like 0.866. I think it's also equal to square root of 3 over 2, I believe, or something along those lines. I can't remember off the top of my head, but that's a good one to memorize for math class. All right, adjacent is Vx. The hip is V, which is 80. So it's very similar to what we had before, right? We'll multiply both sides by 80 kilometers per hour. I'm kind of running out of room over here. Shoot. I'll write it up here. Okay. So what we're going to end up seeing on this side is the 80 cancels the 80. Kilometers per hour cancels kilometers per hour. And we can go ahead and rewrite what we have. Oops. We have Vx then is equal to 80 kilometers per hour times, like I said, about 0.866 times cos 30. I'm going to leave it like that because it's more exact than saying 0.866. All right, 80 times cos 30 is equal to 69.28. This is kilometers per hour. All right, so it's very similar to last time. We see here that the angle is low. It's under 45, so it's not a surprise that our x velocity is the larger of the two velocities. And something we can put in now, right, because this Vx is pointed to the left, is we can put a negative sign in right there. And that tells us left, right? Whereas over here we have a positive sign, and that tells us up. All right, so I'm going to come up here and write this. What do we say? 69.28, negative 69.28. Okay. All right, something like that. And we are done. Okay, so if this was a quiz and I was grading this, I'd look to see did the student draw the vector components correctly, had detailed dotted lines, labeling them Vx and Vy. Did the student then write out the correct formulas, sine and cosine, and solve for the vector components Vx and Vy? And that's about it. So pretty straightforward. Once again, we do this because we can work with these vectors in all in the x direction or all in the y direction, even though they're just part of the actual vector, right, which is 80 kilometers per hour. And then this gets pretty neat to do. So I'll point this out going forward. and how we're going to do it. Okay, so that's about it. Resolving vectors into components. Let's look at the practice. How are we doing on time? Let's see. Okay. The practice, which I handed out in class, and I said you'll probably have to complete the practice as well. And is right here. All right, let's do a few of these together, and then we'll talk about which ones I want you to do. All right, so first of all, there's 3 of these that are super easy that don't require you to resolve into components, right? For instance, let me highlight those ones. This one right here, this one right here, and this one down here. All right, I'm not sure what happened to the Y, the letter Y down there at the bottom there. Okay, so let's go ahead and talk about this. So for this one right here, its x component is obviously 0. And we'll assume, just to keep this kind of similar, we'll assume that all of these magnitudes have units of meters per second. So let's write that at the top. Assume all vectors, well, they're velocity vectors. Assume all vectors represent velocity, or v, right, in meters per second. All right, we're just going to make that assumption going in, make our life easier. All right, so the x velocity here will be 0 meters per second, and the y velocity will be positive 3 meters per second, the positive indicating up. So that's another thing we'll assume. We'll assume that the positive direction, the vertical positive direction, positive y, is up, and that negative y is down. We'll also assume that positive x is right and negative x is left. Okay. Let's look at the next one right here. So in this one, we're going to have an x value of positive 8 for Vx. And Vy is going to be what here? 0, right? Okay. I like writing Vx and Vy with those subscripts better than just writing x and y. So that's how I want you to do it, like this. Okay, cool. Let's go to this one down here. This one's not so bad then. We know that Vx is, well, this point's left, right? Check that out. So this is going to be negative 6 meters per second. And Vy will equal 0 meters per second. Okay.